Hello and welcome to this video. Today we are going to be talking about how to create a new material for use with ExactFlat for Rhino from measured material data. When you send your material out to be measured, you will receive a report that looks like this, and the three main points of data that we need from this report are the Young's modulus bias, the Young's modulus X, and the Young's modulus Y. Older versions of this report don't actually list the Young's modulus bias X or Y as data in the rows and columns here. However, they always have the different equations of best fit for our different material directions here. So the Young's modulus bias X and Y is really just the slope of the line of the equation of best fit. So if you're missing these data points here, or you're using an old version of the report, they're not present, we can look at the material stress strain curve working range graph, and we can just look at the different equations here. So when we click on this one up here, we're looking at the bias graph. So the Young's modulus for the bias direction is 7160.5. It corresponds with what we have down here. The Young's modulus for the X direction is 12,854.96, and again that corresponds with what's down there. And finally, the Young's modulus for the Y direction is 7073.99, which again corresponds with what we have in the report down here. So in new versions of the report, the Young's modulus, they're already pulled off the graph for you, so you can just literally take these values and plug them into the material editor. But old versions of the report, they're not here, so you have to pull them off the graph yourself. So once we have these three values, we can combine them with this document here. This describes in detail how to create a new material from the measured report. It just describes how we pull the Young's modulus off the graph, so that's what we just talked about, and then talks about guessing the Poisson ratio. So in most cases, the Poisson ratio is just going to be 0, and ExactFlat will determine the best way to handle Poisson ratio. The only exception is the Poisson ratio in the bias direction. So if the Young's modulus is in the bias direction is less than the Young's modulus in the X direction, then the Poisson ratio for the bias is going to be 1. Otherwise, Poisson ratio is 0, only in the bias direction. The Poisson ratio in the X and Y direction is always 0. So knowing that, from this measured data, we can formulate three different metrics. So we can simulate the material in a linear bias metric. So that's using the data from all three different directions that the material is stretched. We can simulate the material in a linear orthotropic metric, so using X and Y. And we can simulate the material in a linear isotropic metric. So if the material behaves the same in all three directions, then we can use that. They're all formulated a little differently. The biggest thing to remember is with linear isotropic, we average all three Young's modulus, and that's what we use. With linear orthotropic, we're using the X and Y Young's modulus as is, and then we simulate the shear modulus based off of the linear bias, or the bias direction, the 45-degree direction. And then with linear bias, we just use all three, or all six values rather, all three Young's modulus and all three Poisson ratio values as is. So to create a new material, we go to Rhino, we open up the material. So we click this icon right here, it's the material swatch icon. We click that and it opens up the material editor. It's always going to open up to a new material, so the first thing we're going to do is give our new material a name. So we're going to call it new material. So we haven't added any metrics to this material yet. We do that down here in the metrics section. We click the add button. and now we can choose a metric to add. So using measured data, we can create linear bias, linear isotropic, and linear orthotropic. These are the only three that we can create from the measured data, so we're going to start with the easiest, linear isotropic. So we'll select that from the list and click OK. The only data point that we need that is not on the measured data set is the material thickness. So you're either going to have to measure the material thickness yourself, or in most cases the material data sheet provided to you by your material supplier should have the thickness of the material on there. So you can either pull it off the data sheet or you can measure it. As long as we have the thickness, we can enter that in. Tolerance is always going to be 0. This is more for reporting during optimization, but the tolerance does not have any effect on the shape or quality of the pattern, so we're just going to leave this set to 0. And then for linear isotropic, we need the Young's modulus. So when we look back at the sheet here, linear isotropic metric, Young's modulus is the average of the Young's modulus in the x, y, and bias direction. So we'll go back to our spreadsheet, and we're just going to cheat here using Excel commands. So it's average, and we're going to take the average of all three of those. So we end up with this value here. So we're just going to copy this right into the report here. We're always going to make sure that our units for these reports are always in Newton meters. If ever there's any doubt, these units are indicated on the material as well. So our stress is always measured in newtons per meter. So we just make sure that our units match what's written on the graph here. So it should always be in Newton meters. So. And so that's it for linear isotropic. Our Poisson ratio, according to the document, is always going to be 0. So we've entered in the material thickness, Young's modulus, Poisson ratio, and that's all we need to do. The elongation limit and stress limit, all metrics are going to have limits on them, and these are more for reporting during optimization. They have no effect on the shape or quality of the pattern. So any kind of limit value here, we're just going to leave that set to 0, and we're not going to worry about that. We're going to click the Add button again. We're going to add another metric. So we've already created our linear isotropic. We're going to once again click Add. And we're going to select linear orthotropic from the list. And now we're going to create a linear orthotropic model for this material. So if we go back to our PDF document here, to create a linear orthotropic, we need to use Young's modulus x and y as is for the MD and TD value. And our principal Poisson ratio is going to be Vx, which is always 0. And our shear modulus is either going to be half of or a quarter of the Young's modulus in the bias direction. So this depends on the value of VB right here. So VB is going to be 1 if the Young's modulus in the bias direction is less than the Young's modulus in the x direction, or 0 otherwise. So in this case, when we look at our material data here, Young's modulus in the bias direction is most definitely less than the Young's modulus in the x direction. So in this case, VB is going to be 1. So knowing that, this is going to be half of YB over 2, so essentially a quarter of the Young's modulus in the bias direction. We have all we need to create a linear orthotropic model now. So we're going to go back to our spreadsheet. We're going to take Young's modulus in the x direction. We're going to copy this into the MD column. We're going to take the Young's modulus in the y direction. We're going to copy this into the TD column. And then we're going to go back and we're going to cheat again. We're just going to use Excel commands. We're going to take the bias and we're going to divide it by 4. So we're going to take a quarter of the Young's modulus in the bias direction. And we're going to copy this into our shear modulus value. And our Poisson ratio again is always going to be 0. So we have everything we need. We've entered everything. We're just going to update our thickness here, change that to 1, and that's all we do for linear orthotropic. So again, we're not going to change any of our limits. We're just going to leave this at 0. We're going to leave the tolerance at 0. And all we've done is we've entered in the thickness, Young's modulus x, Young's modulus y. Poisson ratio is always 0. And in this case, the shear modulus is either going to be half of or a quarter of the Young's modulus in the bias direction. And that depends on whether the bias Young's modulus is less than the x Young's modulus or not. Lastly, we're going to create another new metric. We're going to create linear isotropic. So we're going to select linear bias from the list. Click OK, and then we just use all 6 values as is. So again, thickness, we're just going to use 1 millimeter. We'd enter in the thickness of our material. And we go to our report here, Young's modulus x. Copy that into the editor, Young's modulus y. We'll copy that into the editor. And Young's modulus bias. We'll copy that into the editor. Poisson ratio x, y is always going to be 0. X and y is always 0, and then VB, again this is based on whether YB is less than YX or not. We do know that the Young's modulus bias is less than Young's modulus x, so VB is going to be 1. And lastly, we're going to leave all the limits at 0 again, and that's it. We're all done. So the last thing we're going to do is we're going to save our material definition, so we can now use it with ExactFlat for Rhino. So we're just going to save this as new material, and it's very important. We want to make sure we're saving it to this location here. Program data is a hidden folder by default, so you can either type this in explicitly, so we can do C:\program data, or we can use named shortcuts, so program data will bring you to that folder as well. And then we just navigate to TriD Technologies without a dash, ExactFlat Materials, and we can save it right in this folder here. So when ExactFlat starts up, it's going to automatically load every single material in this folder into the material database for use. So saving your new material in this folder means that ExactFlat will load it every single time you want to use ExactFlat, so you can use it in your projects. Thank you for watching. Have a good day.